Next, we have to define the Pascal's law. Suppose there is a container which contains a fluid and fluid is at rest. So the upper surface, which is horizontal, the pressure is equal to the atmospheric pressure. So each point on the upper surface has the pressure which is equal to the atmospheric pressure. Now we take another layer or another horizontal surface which is at a depth h from the surface. So each point will have the pressure which will be equal to the P, and it is the atmospheric pressure plus rho into G into H. This is the pressure due to the liquid column of height h, which we have already defined. That is the pressure at a depth h from the surface. So we can define the Pascal's law that for a liquid in equilibrium, that is at rest, the pressure is same at all points in a horizontal plane. This is the Pascal's law. In other words, we can say that pressure in a fluid at rest is same at all points if they are at the same height. There are many applications of the Pascal's law in daily life. One of the example is the hydraulic lift. This is used to lift the heavy objects by applying the small pressure. Here we take a arrangement such that there is one piston of the smaller area A1 and another piston which is of larger area A2. On this larger piston we keep the object. This is the heavy object, or we can say it is load, and on piston 1 we apply a force F1. This is called effort. Because of this force on the piston which has the area A1, pressure will be F1 by A1, and it will be equal to, because of the fluid and Pascal's law that pressure on the same horizontal plane is same at each and every point. So pressure on the point of the second piston will also be same, which is the P, that is equal to F1 by A1, and which will be also equal to the F2 by A2 if force on the second piston is F2. Therefore, we can write that A2 by A1 is equal to F2 by F1, or we can say mechanical advantage is equal to area of larger piston divided by area of smaller piston, and it is equal to the load divided by effort. So by applying the smaller force, a heavy load can be lifted using the property of the fluid. Let's take some problem. First problem is, a submarine experiences a pressure of 5.05 into 10 power 6 Pascal at a depth of D1 in a sea. When it goes further to a depth of D2, it experiences a pressure of 8.08 into 10 power 6 Pascal. Then D2 minus D1 is approximately, density of water is given, and acceleration due to the gravity is given. Problem is that from the surface of the sea water, at a depth of d1 at a point A, pressure is 5.05 into 10 to the power 6 Pascal. And further, at a depth of d2, there is a point B at which pressure is 8.08 into 10 to the power 6 Pascal. So, height between the A and B is d2 minus d1. Hence, using the formula of the pressure at a depth h, we know that P equal to P naught. This is the pressure at the upper point plus rho GH. Rho GH is the pressure due to the liquid column. This implies that pressure at a point B will be equal to pressure at a point A as per the given figure plus density of water, acceleration due to gravity, and the difference between point A and B, this is d2 minus d1. This implies that d2 minus d1 equal to Pb minus Pa divided by rho g. Pb is given 8.08 into 10 to the power 6 minus Pa is given 5.05 into 10 to the power 6 divided by density is 10 to the power 3 and acceleration due to gravity is 10. So it will be, on subtracting, it will be 3.03 into 10 to the power 6 divided by 10 raised to the power 4, and on simplifying this will be 10 raised to the power 2. So multiplying 3.03 by 10 to the power 2, that is 100, we will get 303 meter. So approximate answer is D. Second question, a liquid X with height 10 cm in right arm of density 3.36 gram per cc is poured in a U tube which contains mercury. Another liquid Y is poured in the left arm with height 8 cm. Upper levels of the X and Y are same. What is the density of Y? First we draw the figure of U tube. On the right arm, liquid X is poured, and on the left arm, the liquid Y is poured. The upper level of the liquid X and Y are same, and the height of the liquid X is 10 centimeter. This is the liquid X. And similarly, height of the liquid Y in the left arm is 8 centimeter. And rest, these two liquids are above the mercury. So as per the Pascal's law, the pressure at the horizontal plane of a liquid is same. Therefore, we consider one of the plane which is at a depth of 10 centimeter from the surface. So this 2 centimeter is the mercury column, and pressure at this point A and point B will be same. So Pa is equal to Pb. This implies that pressure at A will be the atmospheric pressure plus pressure of the liquid column in the left arm, and this will be equal to the density of Y into G into height of the liquid column Y, this is 8 centimeter plus, and now another length is 2 centimeter of the mercury, so it is 13.6 gram per cc for the mercury into G into 2 centimeter, and this will be equal to the pressure at point B, which will be equal to the atmospheric pressure plus the pressure of the liquid column of X, which is having the height 10 centimeter. So it is rho X into G into 10. Pa are on both sides, so they get cancelled. So this implies that rho Y, which we have to find, into G into 8 plus 13.6 into G into 2. This will be equal to rho X is given and its value is 3.36 into G into 10. This G get cancelled. So remaining is rho X into 8 plus 13.6 multiplied by 2, it will be 27.2, and this will be equal to 33.6. So rho X into 8 will be equal to 33.6 minus 27.2, and this will be equal to 6.4. So rho x, density of the liquid x, will be equal to the 6.4 by 8. This is equal to 0.8 gram per cc. So option A is the correct option. Here it is important to note that point A and point B are the points on the same liquid, that is mercury. Hence the pressure on the horizontal plane of the mercury will be same as per the Pascal's law. Next question is, there is a circular tube in a vertical plane. Two liquids which do not mix and of densities d1 and d2 are filled in the tube. Each liquid subtends 90° at the center. Say this is the center O, and angles subtended by these liquids is 90° at the center. Radius joining their interfaces makes angle alpha with vertical. This is the angle alpha. Find that ratio of densities d1 by d2. Suppose the liquid having the density d1 has the length A to B, and it makes angle 90° at the center, and B is the interface of the two liquids of densities d1 and d2, and the d2 liquid has the endpoints B and C. If we drop the perpendicular from A on the vertical line and meets at the point D, so height of the liquid column on the left hand side will be equal to the dE. So we can write pressure at point E from the left hand side should equal to the pressure at E from the right hand side. So on left hand side, pressure at point E will be equal to the density d1 into gravity g and height is dE. It will be equal to, now pressure at point E from the right hand side. So again we drop a perpendicular from the point B on the vertical line, and suppose this meets at point F. So we can write it is having the density d1 into g into, and now height is Fe plus. Now we have to find the height of the liquid of density d2. For this we make a horizontal line from the point O, that is from center, and it drop a perpendicular from C. Suppose this meets at point G, and also we drop a perpendicular from B, and suppose this meets at point H. So the pressure due to the liquid of density d2 will be equal to d2 into G and height will be equal to Cg plus Bh. Now we have to calculate these values of dE, Fe, Cg and Bh from the trigonometry, and we can say that the angle AOD is 90 minus alpha. Similarly, this angle of GOB is 90 minus alpha, and COG is angle alpha. So it is easy to write now that D1 into G into, and DE will be R. R is OE, or we can further explain it. It is OE minus OF equal to D1 into G into, Fe can be written as OE minus OF plus D2 into G into Cg plus Bh. Now we put the values. It will be D1 into G into OE is R, this is the radius of the tube, minus OF will be equal to, this is OD. So OD is R cos 90 minus alpha. That is equal to D1 into G into OE is R, and this is OF, and OF is R cos alpha, plus D2 into G into Cg, and Cg is R sin alpha, plus, and now we remain with BH, and BH will be equal to R sin 90 minus alpha. Now we have to simplify it, because G is common on all sides, so they get cancelled. So, and R also can be taken out. It will be D1 into R into 1 minus cos 90 minus alpha is sin alpha, so it is 1 minus sin alpha equal to D1 into R into 1 minus cos alpha plus d2 into r into sin alpha plus sin 90 minus alpha is cos alpha, and r is common on left and right hand side, so this get cancelled. So remaining is d1 into 1 minus sin alpha equal to d1 into 1 minus cos alpha plus d2 into sin alpha plus cos alpha. We bring this d1 1 minus cos alpha on left hand side, and we will have d1 into 1 minus sin alpha minus 1 plus cos alpha, and it will be equal to d2 into sin alpha plus cos alpha. This 1 get cancelled, so we will have d1 by d2 equal to sin alpha plus cos alpha divided by cos alpha minus sin alpha. Now we divide numerator and denominator both by cos alpha, so we will have sin alpha by cos alpha, it is tan alpha plus 1 divided by 1 minus tan alpha, or we can write it as 1 plus tan alpha by 1 minus tan alpha. Hence option C is the correct option.